Well, now that we've gone through series and sequences of real numbers, we got to now talk about the next step, which is sequences and series of functions. And, well, why are these useful? Well, they have a lot of applications in, say, physics, engineering, other areas of mathematics such as differential equations, and they help us in approximating certain things. For example, how can I approximate, say, the square root of 2, e to the 1/2, or even say sine of 3 degrees. Even how do we approximate those? Well, we can use power series. Power series can help us solve problems that we can't solve analytically, but we can get some good estimates. And we're going to have to develop some preliminaries, and it's going to be based upon some of the things that we saw in the previous chapter, all in chapter 5. And so let's just go ahead and jump right into it. So we have a sum here, but it looks a little different than the sums that we've seen before, except now we have an x in there, okay? So we can in fact regard this as, say, some sort of function of x, okay? But the question is, for which x does this make sense, right? I can't just plug in every single x and get a number that makes sense. Okay, as we saw, we can have sums that converge, sums that diverge. So the way that we have to think about this is we have to consider what's called here both the interval and the radius of convergence. Okay, so let's talk about the interval of convergence here first. So the interval of convergence is where the sum converges, okay? Well, of course, it makes sense for it to be called that. And the interval of convergence, at the very least, is going to be at least an open set. And what does that mean? Well, for us, that just means an open interval. Okay, so we say that the power series has an interval of convergence, say, a minus r, comma, a plus r. And that radius of convergence is the special number r, okay? Now, of course, we may have to check also the endpoints. We may also check the boundaries because we may have something special happen there. Okay, but at the very least, a power series will always converge on an open set. Okay, and the width of that open set, well, rather the radius is, well, the radius r. So how do we handle this? Well, let's first begin with the ratio test, okay? We need to start off with the ratio test. So anytime we're being asked to determine the interval and radius convergence, we always have to start with the ratio test. And remember what the ratio test says, right? We look at the ratio of the next term and the previous term. Okay, an plus 1 over an, we take that limit and see what happens. Well, because now we have a dependence on x, we're going to be a little more delicate here, but let's just go ahead and take a look here on how to handle this. So we're going to use our ratio test here, and I'll just start this in green. So remember that a ratio test starts off with the limit as n goes to infinity of the absolute value of an plus 1 over an. Okay, and in fact here, okay, we have to be a little careful. Okay, all this here, this is going to be our a of n, but it's going to depend on x. Okay, let's move this a little further away. There we go. So our coefficients here, okay, our summands will actually depend on x themselves. Okay, so we're going to go ahead and just follow the pattern here. Switch back to black here. So an plus 1, okay, replace all the n's with n plus 1. So we have x plus 2 to the n plus 1 over 4 to the n plus 1 times, and this is where we have to be careful as always, right? 2 times n plus 1 plus 1. Okay, and then we're going to go ahead and multiply by the reciprocal. Okay, I don't like dealing with complex fractions as you've seen before. Okay, so let me go ahead and move this around here. Okay, remember this is our an of x, okay? So now we have our original summands here, 4 to the n times 2n plus 1 over x plus 2 to the n. We have our absolute value there. And I also remembered that we also need to have our little limit here. So let's go ahead and fix that here. Okay. So remember, we still need the limit as n approaches infinity. Okay. Now let's go ahead and notice that some things will cancel. Obviously, the x plus 2 to the n plus 1 and x plus 2 to the n, those will have some stuff vanish there. So I'm just left with an x plus 2 up top there. Okay, and then it looks like I have a 2n plus 1 on top. On the bottom, well, 4 to the n divided by 4 to the n plus 1. Cancel everything out, I just get a 4. And then I have a 2n plus 2 there, plus 1, so that's 2n plus 3 after multiplying. All right, now let's go ahead and remember that this limit only depends on n, okay? And because this limit only depends on n, anything else that doesn't depend on n can be shoved outside. But because this is all an absolute value, we have to remember that we have to pull anything out with absolute values. Now, of course, the absolute value of 4 is 4, so we're fine there. I can pull that out there. But x plus 2, I have to keep the absolute values there. So x plus 2, an absolute value, divided by 4, times this limit as n goes to infinity of the absolute value 2n plus 1 over 2n plus 3. Okay. Well, we look at that last limit and we say, well, okay, it's equal heavy. Okay, linear over linear. Look at the leading coefficients. 2 divided by 2, that's 1. So this limit is just x plus 2 in absolute value over 4. And you may think to yourself, well, that didn't really tell me anything. Actually, it did. Okay, because remember, for the ratio test, in order to have convergence, we need that the limit, okay, has to be less than 1. So this is the condition that we need to think about here. And so we have to solve this inequality here. Well, how do we solve inequalities? Just the same way we would solve equations. But absolute value inequalities, okay, are a little more special here. So we'll take this thing here, which I'll box in green. Okay. And after I multiply by 4, we get absolute x plus 2 is less than 4. And remember that absolute value inequalities work like this. Let's go off here. Saying that the absolute value of x is less than c means that we have that x is less than c and bigger than negative c. So we're going to go ahead and use that and translate this here. So I have x plus 2 in the middle. That's going to be smaller than 4 and bigger than negative 4. And now I just do the usual thing, right? Okay. So we subtract 2 across. Okay. When I do that, I have x is less than 2 and bigger than negative 6. So at the very least, my interval of convergence, okay? My interval of convergence, okay, x must be between, okay, negative 6 and 2 in order to converge. Okay, I know at the very least, okay, if x is in this interval, okay, possibly excluding the endpoints for now, I have a convergent sum. Okay, so whatever value of x that is in here that I can plug in, say x equals 0, I'll get a convergent sum. Okay, we can show that using, some of the tests that we had before. But now we need to check the boundary. And actually, before we do, let's actually go through and figure out how to find the radius of convergence. Okay. So let's find the radius r. And, well, this is actually very easy to do. The radius of convergence is half the width of the interval. So r is going to be, okay, the right endpoint minus the left endpoint divided by 2. Okay, and if we do all that work, we get 4. So the radius of convergence is 4. Okay, so that's something that helps us. All right. But now we have to check the endpoints, okay? So now we're going to check the boundary for convergence. Okay, we always have to do this, check the endpoints. So what we do is we take our sum here, which I've called f of x, okay, just as a reference point here. And I'm just going to plug in each of the boundary points, okay? Let's go ahead and plug in, say, x equals 2. Well, f of 2, what that looks like here, so we have a sum from n equals 1 to infinity of, so we have 2 plus 2 to the n divided by 4 to the n times 2n plus 1. Well, if we clean some things up here, actually, let me move this over, okay? So if we clean some things up here, okay, in the numerator, I get a weird thing happening there. Okay, 2 plus 2 is 4 to the n, divided by 4 to the n times 2n plus 1 on the bottom. And notice that the 4 to the n's drop, and I'm left with 1 over 2n plus 1. Does that converge or diverge? Well, I'll leave it to you for the details here, but notice here, that looks an awful lot like our favorite harmonic series, right? It does, okay. This diverges. Okay, this diverges, and we need to check by, say, limit comparison test, for example. So we know that at x equals 2, this sum diverges. Okay, so let's just go ahead and cross that out there. Now we're going to check the other endpoint, x equals -6, okay? So x equals -6, we do the same thing. We got something very similar here, okay? So let's just plug in there. So -6 plus 2 to the n, divided by 4 to the n times 2n plus 1. Well, -6 plus 2 is -4. Okay. Notice here, -4 divided by 4 is a -1. Okay, and notice a cool thing that happens here. I have -1 to the n over 2n plus 1. And you should be able to see for yourself that this one, in fact, does converge. Okay, let's put the indices there. This converges, okay, by the alternating series test, by AST. Okay, here we're going to take the helper sequence Bn to be 1 over 2n plus 1, which is certainly positive decreasing with limit 0. So what is the interval of convergence here? Well, we know that the sum converges at the left endpoint, -6, but it diverges at the right endpoint. So at the very least here, we will say, okay, that the interval of convergence, which I'll just call I, the interval of convergence is going to be from -6 to +2, but we're closing it at -6 and opening it at 2. And the radius of convergence, as we saw above, is 4. Okay, so notice the steps that we did here, right? First, you do the ratio test to figure out this inequality here, and you solve that inequality to figure out the interval of convergence. Use that interval of convergence to help you get the radius of convergence, okay, just by taking half the interval width, and then you plug in the endpoints, okay? And everything just reduces to everything that we did in chapter 5. Now, of course, I left off the details here, for example, how to get the conclusion of divergent here by the limit comparison test, and how to get the convergence here by the alternating series test, okay? Those are left for you to go back and review, okay? Now, of course, for the limit comparison test here, just compare against 1 over n, right? You'll see that the limit is 1/2, and we know that the sum 1 over n diverges. 1 over n is not summable. So by comparison, this guy here on the left is not summable, but this one here, okay, on the right is indeed summable, okay, by the alternating series test. Okay, so you see how all that stuff in chapter 5 is coming back, right? We need these as tools, okay? But the first tool that we definitely need is that ratio test. And so let's practice with another one here. Okay, just another simple one. Find the radius and interval of convergence. Okay, so we have 3x minus 1 to the n over 6 to the n times n minus 1. So we're just going to go ahead and start off with the ratio test. Okay, that's always step 1 for these problems here. Start off with the ratio test. So I want here the limit. Let's make that look a little nicer here. So the limit, as n goes to infinity, of the absolute value of, and remember how I like to write these, right? Put in the n plus first term and then multiply by the reciprocal of the original, okay? Just to avoid the complex fractions. So we'll have 3x minus 1 to the n plus 1 over 6 to the n plus 1 times n plus 1 minus 1, okay? Please remember how to be careful with those replacing n's with n plus 1s, okay? Just like you would with your x's and x's plus h's, right? Okay. Now we just put in the reciprocal of the original thing here. Okay, and you might already see the punchline maybe here. Okay, some stuff will cancel, right? Notice here that I have n plus 1, 3x minus 1s, and n of them down here, so those can drop. Okay, and I have a 3x minus 1 left over, which is independent of n, so I can throw that outside of the limits here, but remember what the absolute values, right? Okay, now let's see what else is left over here. Okay, I have 6 to the n rather, and 6 to the n plus 1. Okay, common factors can go away. And now I can pull that 6 in the denominator out, and absolute value of 6 is 6, so we're safe there. Okay, so that comes out of the limit as well. And I have this simple looking limit here. N minus 1 over n, that's a calculus 1 limit. We know how to do that, right? if you divide, right, 1 minus 1 over n, that goes to 1. So I'm left with this here. This inequality that we have to solve. I need this to be less than 1. Okay? So remember, let me fix that here. Remember that with the ratio test here, in this context, we're trying to find the condition that needs to be satisfied, okay? Because this inequality is going to depend on x. Only certain x's will make sense in this one, okay? So we'll go ahead and do the solving of the inequality in the same way. In fact, this one's actually kind of a simple one, so let's do this off to the side here. Okay, so we multiply through. So we have 3x minus 1 in absolute value is less than 6. Okay, and then with the absolute value less than the number, we just make that compound inequality minus 6 on the right, on the left, the thing in the middle, and 6 on the right. And now it's just the usual game, right? We add 1. Okay, and then divide by 3. So now our interval of convergence, at the very least, we know that our sum converges on this open set. Okay, our sum is convergent on this open interval. Minus 5 over 3 to 7 over 3. What's the radius of convergence, you might ask? Well, okay, let's do that here. So the radius of convergence, okay, right endpoint minus the left endpoint divided by 2. Okay, and well, how does this work out, okay? 7 over 3 minus a minus 5 over 3. 7 plus 5 is 12. Divided by 3 is 4. Over 2 is 2. So the radius of convergence is 2, okay? So that gets us somewhere. Okay, so we know at the very least here, okay, we know that our interval of convergence, our interval of convergence is this interval. Let's change that to a 5 like it should be, okay? This is our interval of convergence at the very least, okay? We know that the sum will converge on this open set, but we still have to check the boundary, okay? So we still have to check the boundary, okay? So we'll go ahead and plug in x equals negative 5 over 3. Okay. Now again, you want to regard this as a function. You want to see if I plug in a certain number, we'll get a number that makes sense, okay? Meaning a convergent sum. So let's go ahead and take a look here. So if I look at this here, okay, the sum starts at 2 now. Okay. So let's take a look here. 3x minus 1. So let's just do it like this. 3 times negative 5 over 3 minus 1 to the n over 6 to the n times, let's see, n minus 1. There we go. All right. Well, 3 times minus 5 over 3, the 3's drop. Negative 5 minus 1 is negative 6. Okay. And I'll show this extra detail that I didn't in the last problem here. So we have negative 6 to the n over 6 to the n times n minus 1. Okay, again, remember these exponent rules, right? If I have two things with the same exponent, one on top, one on bottom, I can just shove them into one exponent. Well, negative 6 divided by 6, okay. Whoops. We are losing a lot today. Okay, here's just the extra detail, okay, just to show it, okay. Negative 6 over 6 to the nth power. Well, negative 6 divided by 6 is negative 1, okay. And now take a look at what I have here, okay. Negative 1 to the n over n minus 1. Now, does this sum converge? That's our question here. Well, the answer is yes, okay? This converges by alternating series test. This converges by the alternating series test, okay? Here, we're going to take the helper sequence Bn to be 1 over n minus 1, okay? And that's nice, right? That sequence, that helper sequence, okay, is positive, it is certainly decreasing, and the limit is 0. So by the alternating series test, this guy converges. We actually know what the number is, but you'll find out what it is later. All right, so we know that we'll give this a check mark here. This sum converges at the left endpoints. But now let's check the right endpoints, okay? So now we're going to check x equals, what is it, 7 over 3? So we'll do the same thing here, except now I'm going to plug in 7 over 3. All right, and you can probably already see what's going to happen, right? 3 times 7 over 3 is 7, minus 1 is 6. Let's just write that out. Okay, 6 to the n over 6 to the n times n minus 1. The 6 to the n's drop. I have 1 over n minus 1. This is the harmonic series again in disguise. It's just shifted a little, okay? You can re-index here and you see, oh, that's a p-series with p equals to 1. So by the p-series test, we know this thing's divergent, okay? This diverges. Okay. But of course, you could also do this by the limit comparison test against our favorite 1 over n. Okay, so this sum diverges at 7 over 3. So let's conclude here. The interval of convergence I, okay, is negative 7 over 3. Nope, negative 5 over 3. Getting my numbers mixed up here. Negative 5 over 3 closed there, but it doesn't converge at 7 over 3. Okay, so close at the left endpoint, open at the right. With the radius of convergence R equal to 2. Okay. So again, very, very simple, right? Just very simple. Okay, we're just going back to what we did in chapter 5, except now we're relating these back to functions. Okay. So again, do the ratio test, solve this absolute value inequality here. Okay. Get your radius convergence, test the endpoints, and then use your methods from chapter 5. Okay. You want more details from these? Okay, go back and watch those convergence test videos. Okay, go back and watch those and go back and review those. All right, we got one more here of this type, but we got a square root now, and there's a minus. Okay. So how do we handle this one? Well, same thing. Start off with the ratio test. All right, so we're looking at this limit here. As n goes to infinity of, replace the n's with n plus 1s, okay? So negative 2 to the n plus 1 times x plus 3 to the n plus 1 divided by the square root of n plus 1 plus 5. Let's just write that in. Okay, now take the reciprocal of the original. All right, see, ratio test, our favorite one of the most powerful ones to use. All right. Now let's notice some things. Okay, negative 2 to the n plus 1 divided by negative 2 to the n gives me just a negative 2. Okay. And of course, x plus 3 to the n plus 1 divided by x plus 3 to the n just gives me an x plus 3. All right. And with that x plus 3 left over, okay, I can just go ahead and pull that out of the limit with the absolute value. So I have an absolute x plus 3. But now notice, okay, I also have a negative 2 that's still in there, but I need to pull that out as a 2, okay? Because the absolute value of negative 2 is 2, okay? In fact, let's kind of move this down just a little bit here. There we go. All right. We have this times the limit as n goes to infinity of the absolute value of square root n plus 5 over square root n plus 6. Well, it's basically a square root over square root, right? To show you just like the extra detail, let's go ahead and do this here. We have 2 times the absolute value of x plus 3 times the limit as n goes to infinity. I can put that under one giant square root. And of course, I can pass limits through continuous functions, okay? Absolute value is continuous, square root is certainly continuous. But look at the inside there. N plus 5 over n plus 6, those are basically the same. Okay, it's equal heavy. Leading coefficient is 1, so the limit there is 1. So I have 2 times absolute x plus 3. And in order for this to converge, I need this to be less than 1. Okay, let's put that keyword there. I need that to be less than 1. All right, so let's go ahead and solve the absolute value inequality here off to the side. So 2 times absolute x plus 3 is less than 1. Let's go ahead and divide both sides by 2. So that I have, so that I have absolute value of something is less than a number. Okay, now we just play the same game, right? Minus on the left, plus on the right. Just familiar stuff from algebra. Now subtract 3, right? Well, let's see. Negative 1/2 minus 3. Remember that 3 is 6 over 2. So negative 1 minus 6 is negative 7 over 2. then an x there, okay, and then 1 minus 6 is minus 5. Hey, didn't we have an interval just like this before? We almost had something like it, though. Okay, let's double check here, okay? 1/2 minus 3, 1 minus 6 is negative 5. Yep, okay. So this is our interval of convergence. So we know at the very least, okay, our sum will converge on this set, on this open interval. But we have to check the boundary. We have to check the boundary. We have to check the endpoints. So let's go ahead and check the boundary here. First, okay, -7/2. Okay, we're just going to plug that in. Okay, plug that into our original power series. So let's see what we have here. The sum starts at 1. I have -2 to the n. Okay. Whoops. Switching apps all over the place, right? Okay. And then we have -7/2 plus 3 to the n divided by square root of n plus 5. Okay, well, -7/2 plus 3, okay, that's -1/2. Okay, check it, all right? So we have n equals, sum from n equals 1 to infinity, -2 to the n times, well, let's see, we got a -1/2 inside there to the nth power over square root of n plus 5. Okay. Well, take a look here, right? I can just cram those into the same exponent, right? Into the same base. Now take a look here, right? -2 times -1/2 is 1. And 1 to the n is just, well, 1. So now I have this here. Does that converge or diverge? Well, that looks an awful lot like 1 over square root of n, which you can make it look like after a reindex, right? And it turns out that this sum is actually divergent, again, by the p-series test. Okay, so this is divergent. Okay, by limit comparison. It's divergent by limit comparison against 1 over square root n, okay? Remember, for limit comparison, if you discard any lower order terms here, like if that 5 wasn't there, well, we know the result by the p-series test, right? So make it look like a basic series that you know. So this diverges at -7/2. Okay, now we have to go ahead and do the same thing here, okay? So now we're going to go ahead and check the other endpoint. X equals -5/2. Okay, I just realized we didn't get the radius convergence. We'll get that in a second. So we plug in -5/2, see what happens. So n equals 1 to infinity. -2 to the n times -5/2 plus 3 to the n over square root of n plus 5. Well, -5/2 plus 3, okay, that gives a 1/2 in there. And then, well, let's just write it in, okay? So we have this, -2 to the n times 1/2 to the n over square root of n plus 5. All right, so, well, -2 times a positive 1/2 is a -1. So now I have this. Now you might be tempted to say for this one that this one also diverges, but remember, this is an alternating series, and alternating series can have some very special behaviors, okay? Well, think about the helper sequence here. Okay, the helper sequence here is 1 over the square root of n plus 5. It's certainly positive. It's certainly decreasing, okay, because I'm doing 1 divided by bigger and bigger numbers, and the limit is 0. So by the alternating series test, okay, this converges. So this converges by the alternating series test. Okay, this converges by the alternating series test. So at -5/2, we'll get this a check mark. So what is our interval and radius of convergence? Well, our interval of convergence, it doesn't converge at the left endpoint, but it converges at the right endpoint. Okay, so we close it there. But what about the radius of convergence? Remember, the radius of convergence is just the width of the interval divided by 2. So let's show that work there. -5/2 minus a -7/2 divided by 2. Well, -5 plus 7 is -5 plus 7, okay, is a +2 Okay. And then we have 2 divided by 2, which is 1 over 2. So the radius of convergence is 1/2. Okay. You can see that the width of the interval is 1. And so the radius of convergence is 1/2. Okay. So that's all the information that we need to get there. Okay. So once again, let's just outline the steps one more time. Okay. Start by looking at the ratio test. Okay. You're going to have something that depends on x, and then you need to get this inequality here. This one's important, okay? We need this to hold, okay? Whatever result that you get, if you get something that depends on x, okay, then that means that you need this inequality to hold. You need that thing to be less than 1 in order to converge by the ratio test. Then at the right there, we solve the absolute value inequality. It's just something from algebra. Then we test the endpoints. Okay, use all the stuff from chapter 5, okay? And then you can determine your interval and radius convergence, okay? Now, of course, these problems didn't really have them here, but if for some reason you get that the limit here is 0 no matter what, okay, then your radius convergence is infinite, okay? It converges for all real x, okay? Possibly for complex x, okay? But if if this limit here turns out to be 0 no matter what, well, 0 is always smaller than 1. So your radius convergence is infinite, and your interval convergence is the entire real line. Okay. There are also cases where you might have a sum that converges only at a single point. We say that the radius of convergence is 0 there. Okay. So we might see some examples of that in the homework set. I want to do one last one here just to test this point home here. You may have noticed a small cut here. Sometimes we do things, sometimes we prepare, and then sometimes we realize that, we only have an old version. But let's just recap everything that we did, right? You need the interval and radius convergence for power series. Do the ratio test. Solve an absolute value inequality. That will tell you your interval convergence. From that, you can get your radius convergence. Just take the interval width and divide it by 2. Test the endpoints. Use chapter 5. That's all you need. Okay, in the next part, we're going to go ahead and look at some basic constructions of some basic power series. Some things that may look very familiar. I'll see you in the next one.